Hey, welcome back to your favorite calculus class. We're going to take a look at the second derivative test and curve sketching. So here, I want you to notice that the graph here, see how it's kind of smiling up here? That's what's called concave up. Over here on the right, see how that is concave down? It's kind of flipped over U, if you will, concave down. That's what we're going to talk about in the second derivative today. So I want you to think about for a minute what the derivative is doing here. Notice on this first one. See that slope of the tangent line? Let's give that an actual value. Let's pretend for a minute maybe that slope of the tangent's negative a third. And then notice this slope of the tangent right there. Maybe that's like, it's positive, but let's call it 1. And then see how it's a little steeper? It's still positive on that next slope of the tangent right there at that point. Maybe that's like 3. But if you notice, if negative 1/3, and then it goes up to 1, and then it goes up to 3, the derivative is increasing. The value of the derivative is increasing there, right? So you remember how last section, if we said when the derivative is increasing, right, then the original function was increasing. Now this is, the derivative is increasing, so the derivative of the derivative is positive, is increasing, if you will. So if f double prime is positive, you're going to be concave up. That's what that's showing us there. That since the derivative is increasing, right, f double prime is positive. In other words, we know f double prime is positive. Then that's telling us that the original function is concave up. Now over here on the right-hand side, maybe let's name a few of these. Maybe this f prime is like negative a third, and this f prime is like negative 1, and then this f prime is, let's say, negative 4. Can you see how the f prime is decreasing, which means f double prime is negative if f prime is increasing. So in other words, we are concave down. The original function is telling us that the original function must be concave down. Okay? So that's kind of an introduction to the second derivative test. If f double prime is positive, graph is concave up in that interval. If f double prime is negative, which means f prime is decreasing, right? If f double prime is negative, that means f prime is decreasing. That means it'll be concave down, right? And then we're going to find these Hergert numbers, and these are points where the derivative is 0 or undefined, but it's got to be defined. That's a Hergert number, and we're going to test around those for our second derivative test, okay? And then an inflection point is just where the concavity changes around a Hergert number, okay? So let's go ahead and do it using the graph here. Using the graph, where is this? Let's go with concave up first. Can you see that it's concave up, is smiling up, if you will, from an x value of 1 on? See how it's concave up? It's up, right? In other words, f prime is increasing, is what that's saying. Right? If you take the slopes of the tangents on that interval, they'll go up in value. F prime is increasing. Where is it concave down? Let's do that in green. Can you see how it's concave down? Flipped over, if you will. Concave down from negative infinity up until that x value of 1. Okay? So we have an inflection point where? Right where the concavity changes. So at 1, 0 would be where this has an inflection point. Let's do another one. Here, Can you see that this is kind of smiling up, if you will? You're concave up from negative infinity to 0. But over on this right-hand side, see how it's kind of going down, concave down from 0 to infinity on that right-hand side. Pointing down, if you will. Do you have an inflection point? You do not, because you've got a vertical asymptote. Even though it changes from concave up to concave down, it's not defined at 0. So there's no inflection point. Why? Because that's not a Hilbert number. It's not defined there between them, right? So even though concavity changes, you got to be careful. It has to be defined in order to have an inflection point between them. Now let's go ahead and do some algebraically, okay? So here we've got this function. I'm going to go ahead and multiply that through. So I've got f of x is x to the 4th minus 4x cubed, right? And it's just asking for points of inflection and where it changes concavity. So I'm going to take the first derivative, but I'm going to leave it. I'm not going to analyze it with the first derivative right now. I'm just going to go straight to my second derivative so that we can analyze concavity. So 4 stays there. I get 12x squared minus 24x. Let's find our Hilbert numbers. Let's take 12x out. I have x minus 2. And so 12x equals 0, x minus 2 equals 0. So I get x being 0, x being 2. As long as 0 and 2 are defined in the original, which they are, 0 and 2 are both defined in the original, these are both Hilbert numbers. Okay, so we want to go ahead and we would run our second derivative test, testing around those Hilbert numbers. So let's go ahead and throw in negative 1. So f double prime of negative 1. And I'm going to throw it into my second derivative. So I got 12 times negative 1 times negative 1 minus 2. I got negative 12 times negative 3, which is a positive 36. So f double prime of negative 1 is positive. So if it's positive, if the second derivative is positive, which again means the first derivative is increasing, right? If the first derivative is increasing, that means we're concave up. The original function is concave up on that interval from negative infinity up until 0. Now I'm going to throw in something between 0 and 2. How about 1? F double prime at 1. So I throw it into 12 times 1, throw it into the second derivative. So it looks like f double prime of 1 is negative. That means we're concave down. The original function must be concave down between 0 and 2. And finally, let's throw in like 3. F double prime at 3. I got 12 times 3 times 3 minus 2. F double prime at 3 is positive. So we are concave up after 2. So let's go ahead and write these down. We are concave up from negative infinity to 0, as well as from 2 on. We're concave down between 0 and 2. Do I have inflection points? Yes, because those are Hilbert numbers. That means they're defined on the original function. And wherever it changes concavity, notice I changed concavity at x being 0. So that would be the point 0. Plug it into the original function, which would spit out 0. And I changed concavity from concave down to concave up at x being 2 as well. So that would be the point 2. Plug it into the original. 2 cubed is 8. 8 times 2 minus 4. 8 times negative 2, negative 16, it looks like. 2, negative 16. Again, plug those into the original function to find those values for your points of inflection. All right, let's look at this next one here. We've got, I'm going to take the first derivative. I've got 8x to the 3rd minus 8 plus a 0. I'm going to go directly to the second derivative because it just is asking for our concavity and inflection points. So I get 24x squared minus 0. Let's see if we have any Hilbert numbers here. 5 by 24, square root, square root. So x is plus or minus 0. Of course, that's just 0. Make sure 0 is defined in the original. It is. So this is a Hilbert number. It is defined in the original function. We're going to go ahead and test around it. So the second derivative test around this 0. And let's go ahead and throw in negative 1. We'll throw it into the second derivative. So we have 24 times negative 1 squared. 24 times 1 is just 24. So it's positive. That means we're concave up. The original function is concave up. Let's throw in f double prime of 1. 24 times 1 squared. That is also, second derivative of 1 is also positive. So that also means we're concave up again. Okay. So let's write this down. We're concave up from negative infinity to 0, and then also after 0. Okay, there's no concave down, not applicable on this. Did it change concavity at 0? It did not, right? I went from concave up, and then I went concave up again, right? So it did not change concavity, so there's no inflection point here. And I should add, x being 0 is a Hilbert number, but it's not a point of inflection because the concavity did not change. Now here, notice we're asking about everything. Where are you increasing, decreasing, relative, min, max, all that stuff. So we're going to have to analyze the first derivative, and then we'll analyze the second derivative, right? So we use both tests on this one. So let's take here's our function, y equals negative a third x cubed plus x minus 2/3. And let's go ahead and take the first derivative. Where's this equals 0? So I got negative 1x squared plus 1. So we got plus or minus 1 on this. These are critical numbers. They are defined in the original. So let's go to our first derivative test. Negative 1 to 1. Let's throw in like y prime of negative 2. And I throw that in. That'll be less than 0. So the original function is going to be decreasing. Let me throw in y prime of 0. Again, I'm throwing it into the first derivative here. And so that'll be positive. So now the original function increases between negative 1 and 1. And finally, I'm going to throw in y prime of 2. And that'll end up being negative, right? And when you're throwing those in, of course, be careful. You've got negative, and then you got the 2 being squared plus 1. So the negative stays out front. Negative 4 plus 1, negative 3. So again, decreasing. Right? So I have critical numbers, negative 1 and 1. I'm increasing between negative 1 and 1. I'm decreasing from negative infinity to negative 1. And I'm decreasing from 1 down. I have a relative max at 1, at x being 1. I throw that into the original. I get negative 1/3 plus 1 minus 2/3. That would be 0. Throw that into the original function. I have a relative min where I decrease and then increase. So that'd be at negative 1. I throw negative 1 into the original function, and my relative min will end up being negative 4/3. Okay, so we've answered all the first derivative test stuff here. Now let's move into our second derivative. So number 2, we have y prime as negative x squared plus 1. Second derivative equals negative 2x. Where do I have a Hilbert number? Take that second derivative equal to 0, x being 0. Make sure that that is in the original function. It is defined. So here's our Hergert number. We want to test around that. So our second derivative test around 0. Let's throw in y double prime of -1. Throw it into the second derivative. So we get -2 times -1. Y double prime of -1 is positive. So we are concave up. Let's throw in y double prime of 1. -2 times 1. So y double prime of 1 is negative. So we are concave down. So we're concave up from -infinity up to 0. We're concave down from 0 on this thing. So there's our concavity. Did we change concavity? Yes, we did. So that x being 0 is a point of inflection, that Hergert number. So I plug that into the original function. So I throw it in up here, throw 0 in, I get 0 plus 0 minus 2/3, so I got -2/3 on that. There's our inflection point. And then our x-intercept. Well, what's our x-intercept here? Our original function is -1/3 x squared plus x, or x cubed, sorry, plus x minus 2/3. Where's our x-intercept? Where's y equal to 0? X cubed, good grief, plus x minus 2/3. And we could solve that down to find our x-intercept. So let's see. 1 would go into that. I'm going to multiply this by -3, so I'd have x cubed minus 3x plus 2. And then that'll actually factor, let's see, that'd be so I've got x being 1 with multiplicity of 2. That's one of my zeros. All right, there's 2 of those. And then at -2, 0 as well. Let me put those points on the graph. 1, 0. Now, if it has an even multiplicity, I know it just touches either from the bottom or from the top. And then -2, 0. Now let me find my y-intercepts by letting x be 0. So throw 0 in for x. That'll spit out -2/3, which is also our point of inflection. Okay. So now we can kind of put everything together. So if I kind of zoom out a little bit, I'm like, okay, I'm decreasing from -infinity to -1. And I'm concave down. So I'm going to draw the concave down until, or I'm sorry, I'm concave up. So I'm decreasing -infinity and -1, and I'm concave up until 0. And let me put on my graph here 0, -2/3, about right there. So I'm coming down, I'm decreasing, -1, but I still stay concave up until 0. And then I change concavity. Let me go concave down after that, hit that relative max, and then I'm decreasing after 1. Let me erase this little piece right there. And that's a pretty decent graph there. I should have wrote in my Hergert number was x being 0. And that kind of puts everything together for us on the graph.